Great. So let's start today. This is the uh, second session on coalition game theory. And as we discussed, there are games, there are settlements, there are auctions. And one important things are coalition game theory. We defined some important concepts previous time about submodularity, supermodularity, convex, pre-imputations, feasibility, etc., as well as some criteria for fairness. Today, we are using those concepts in a sense that we are essentially giving some insight into coalition game theory based on those concepts that we discussed previously. And one important thing that we will talk a lot today about the Shapley value that plays an important role here because it's a very important one. And interestingly, this is a game theory. Game theory and machine learning in general and AI, of course, game theory is part of AI in some sense. But more importantly, game theory and ML also have lots of connections. And one of them actually done through Shapley values. We will talk about Shapley values when you are doing any machine learning algorithm. Generally, you have, some features, even in neural nets, we have the features. And the question is that how important is this feature in predicting essentially the future or the predicting on the test data or future data. And that's the one that actually there's a paper that is defined this one, connects this one, and use Shapley value. And it is a very common standard nowadays in industry to use this one, and there's the packages for that. If you just Shapley value for ML, then you will get it. And then it's a general approach that for different approaches that exist for machine learning, like, I don't know, decision trees, a random forest, XGBoost, LightGBM, you name it, linear regression, etc. You can actually get the Shapley value to say that what are the features who are important. Good. And with this introduction, let's talk and define what is Shapley value. Good. So, Shapley value of a game so first you remember that we define pre-imputation, and what was the definition of pre-imputation? Is a payoff division that is both feasible and efficient. Essentially, what's the meaning of both feasible and efficient? It means that any payoff that you will get it, divide it completely among the people on that coalition. This is the theorem. So this is in some sense Shapley value is, I believe actually Shapley also got the Nobel Prize in econ. And one important thing that he has is this essentially Shapley value that he defined. It has lots of good properties that we discussed before. Given a coalition game N and nu, N is the number of players, nu was the characteristic function, that the payoff function. There is a unique pre-imputation, essentially psi of N and nu, that satisfies these properties. Symmetry. You remember that what was the symmetry is that two agents have the same effect on the payoff when they are added to coalitions, they should get the same payoff essentially. Like when we are essentially when we divide the payoff among the players. Dummy player, that we had the definition of the dummy player that, if a person, anytime that it's doing the extra value, the marginal value is the value of that person itself, also that person gets that as its payoff. And then additive axiom that if you can write the games, essentially somehow summations of two games, then the payoff also should be summation of these things. And of course, it is a pre-imputations as well. It means that it divides the money, the payoff, completely among the players. So it has lots of good properties. That's essentially the thing that Shapley value is considered a very good one. The pre-imputation, and it satisfies symmetry, domain player, and additivity axioms. And that is for each player, I's share is this formula. I say, okay, what the hell is this formula? We will talk about that. Why this formula actually is very intuitive formula. So this amount that each person gets, the person I gets in this game, is called the Shapley value. And that is introduced by Lloyd Shapley in 1953. What is this formula? This formula is the I's average marginal contribution. What's the meaning of that? We will define it and then it becomes very intuitive, even though it's not maybe right now. The average contribution, what is this one, the average marginal contribution? The average contribution that I makes to the coalition, average over all possible sequences. Essentially, when you have number of sequences, it is like n factorial if there are, guys, that's the thing that you have lots of factorials here, in which the grand coalition can build up from the empty coalition. So essentially, you try to build a grand coalition, and you want to say all possibility that you can do that, and you will take the average over them. So let's see this. So suppose agents join the grand coalition. So these are like essentially there are n people. Say that they are joining in the coalition one by one. And all sequences have the same probability, essentially same probability of appearance. How many sequences do we have with n, essentially n players? If we want to consider all possible sequences that we can build this grand coalition, and we talk about the grand coalition, there are n factorials. N factorial sequences, so the one that each one of them it appears is 1 over n factorial. Now, let's at any time, so we are doing the first agent, agent 1, agent 2, and so on. Say S with the agents that joined before I. So this is the AI essentially. Say this is S in some particular sequence. Consider those that are essentially joining before agent I. This is, consider them S. And TB, the guys, so AI plus 1 to AN, this would be the T essentially. What is the marginal value that I is doing? Marginal value is always defined, as we have defined it before, for the submodular functions or supermodular function, nu of S union I minus nu of S. How much I adds to S? And this is independent of how S is ordered and independent of how T is ordered, because these are the people who are there. So now, what is the probability that first we have S, then I, and then T? So that would be the number of sequences that include S, then I, and T over the total number of sequences that was n factorial. So how many ways, I mean, if we have S and T, for a particular S and T, that here actually, if you see, we sum over all possible sets S that does not contain I. So the T would be the remaining essentially. S n minus S union I. So in that case, We have S factorial options here for the ordering and T factorial options here. And then AI is the thing, so we don't have any option because that should be agent I over N factorial, which is the total number of, actually this should be size of T factorial and size of S factorial times N factorial. So this is the one that we have it. So for agent I, you have S factorial. Now, what is the size of T? Size of T would be N minus size of S minus 1, because agent I factorial over N factorial. What was the marginal things that in this case I add is this amount that we took. So the expected contribution over all possible sequences, or you can say is the average over all sequences, is that we are just summing it up over all S. So you are doing all S. This is the value that it gets, and that would be the part that agent I essentially is. So that essentially comes from this formula. This part is essentially some probability, and this part is the marginal value. So that's a very intuitive, actually, formula that he is defining. Good. Let's see some examples. Example from the previous week, or previous session, actually. This is the voting game example. So say there are 3 parties, and say here, in this case, we can consider each party as a whole, like a player. So in some sense, there are 4 players here. We can consider each person in the party as a different player, but because they are somehow colluding, maybe easier to consider these 4 guys as the players. So I have parties A, B, C, and D, and they have this number of representatives. So a simple majority, 51 votes. We have discussed different things. So 50, 51, but say here 51 votes is required to pass the 100 bills, 100 million bill. So this is the idea. How much money is it fair for each party to demand in this case out of this 100 million? So here we are just calculating the Shapley value of the game. So as we discussed, every coalition that has at least 51, because it should be the majority, has value 1. Every other coalition has value 0. In that case, it's a simple game. So let's get some ideas about this kind of fairness thing that we discussed. If you remember, we said that for 2 agents I and J, they are interchangeable. If for every S that contains neither of I or J, essentially when you add I to S versus when you add J to S, the nu would be the same. Like, of course, before adding both of them would be nu of S, after them it should be the same. So here, let's see what are the things. For example, so this is the nu function that we have defined, correct? This is the nu function. So, and again, here we have like 4 parties, 4 players. So here, B and C are interchangeable. Why? Let's see, what are the all possible cases for S? So, if it is empty set, they will not add anything because B and C, both of them are 25 and 15, less than majority. If you consider S to be A, then they are adding 1 to that, because in both cases, they make essentially this one over the majority. If it is D, D is only 15. They both added and cannot do anything to D. Still would remain 0. And if it is A and D, they are already majority. So again, the value of them does not add anything. So you can say the same thing. So essentially, here we had it B and C, but also B and D, because these are the same number. Essentially, they play the same things. So here, as well as if you are doing C and D, all these three pairs are interchangeable. So the fairness axiom says that B, C, and D should each get the same amount. Because the two people are interchangeable, then we should have this kind of like symmetry between them, and then we should both should get the same. So now let's calculate the formula, just this one. So this was the formula. This is the phi of I and S was this formula for this particular. So essentially, like phi of I and S means for agent I and any set S, for a particular set S. That was the formula that we had, and this phi I of the whole game essentially is summation over O SS. So here, I mean, to simplify the issue, we can define just another variables that instead of dividing by n factorial, like just consider this one and times n factorial to become everything becomes essentially integers. So let's compute this one. And of course, we can get a phi of is by just dividing this number over n factorial. So let's compute just one example, phi of A for agent A and n and the whole game essentially. So n in this case would be 4 because there are 4 players. Now, what would be the phi prime of AS would be n factorial here. So n factorial will cancel that n factorial. Then we have s factorial. What is n minus 1 minus size of s would be essentially 4 minus 1, which would be 3 minus s. And this is the marginal value. Let s be any of these things. So now this is essentially the one that we define. And again, this formula, we had some multiplication by n factorial. We divide it by n factorial at the end. Then you will take different s's and you just compute it essentially. So in this case, and so what is the final formula that you have? So for agent I, if you want to do it, you will say 1 over n factorial essentially is this part. So this is essentially the phi prime of I and S. Phi prime of I and S. Good. So you just divide it over n factorial. So you can compute these ones. So you can just compute this one. We just remember that A has 45 members, B has 25, C has 15, and D has 15. So just let's compute this one essentially for different S. So so this we are just computing for agent A, and then you put S. So then what is the marginal value of essentially S would be A would be nu of A minus nu of empty set, which would be 0 minus 0, which is 0. You will compute it for all of these guys. These are the numbers, and you just take this. And then what would be the phi prime in this case? Then we knew that it was size of S, which is 0 here, times 3 minus size of S, which is 3 factorial. So 0 factorial, 3 factorial, and 0 factorial is 1. Yeah, sorry, 0 factorial is 0 actually. And 3 factorial is 6. And then you have 0 at the end because the marginal value was 0. So you will compute all of these guys, and then you will take the average. 1 over 4 factorial, which is 1 over 24. And what do you get? So you just compute this one and you get 1/2. Just a formula and then 1/2. Good. Now, this one was for A, that you will get it essentially 1/4. So that was the phi of A. And you don't write the game when it is clear from the context. It would be 1/2. And then if you compute for phi of B, C, and D, it would be 1/6. And that was expected because, I mean, these guys essentially were interchangeable. So Shapley value theorem says that they should get, and because they satisfies the axiom of symmetry, they should get the same value. So we get 1/2 and 3 1/6, which is 3/1/6 would be again 1/2, 1/2 plus 1/2, it would be equal to 1. And that was the pre-imputation things, that the sum of these values that these people will get it would be equal to 1, or the whole value of the game, which is 1 in this case. And again, I mean, if you wanted to compute it, you didn't need to, you can write the formula, but if you want to do it in a smarter way, you can say, okay, these people were symmetric, B, C, and D, all of them were symmetric. It means that all of them should get the same value. So you can just say half of that goes to A, the remaining half, which is the remaining half should be divided equally between 3 guys. It means that each of them should get 1/6. So you really don't need to use the formula. You can just use this kind of symmetry property to get the result that you want. So that is the thing. So if you want to distribute the money, it would be the case. A gets 1/2 of 100 million, B, C, and D, each of them get 1/6, which is this. So that's essentially the way that the Shapley value is giving or distributing this money among these agents. Good. Now, I want to give another example of the Shapley value. The Shapley value, I mean, generally it is the case when you have some kind of machine learning things, generally you have this kind of the features, I will call it x1, x2 to xn. You want to get some y out of it. So that is the general concept of machine learning, that you are given essentially, you want to compute this f of x, vector of x, which is y. What do you have? Generally, you have some kind of train data, and then you have something like test data. And maybe there are some other things that are, these are the future data. Essentially, that's the whole task of machine learning. You are given this kind of x1 to this one that we call them features. And then these are different, essentially like x1, x2, x3. Each column of this, essentially, each variable is corresponding to a feature. Like, what is the value of x1 means what is the value of the feature 1, what is the value of feature 2, etc. Or what is, yeah. And then from that, you want to get y. Y is the function that you try to predict by training your system or your model. So that's the whole task of ML, essentially. Good. Now, in this case, actually, you can define these whole things as a game. I say these are the game, and you want to see how much each of these features are important. The feature 1 versus feature 2 versus feature n. For example, I mean, you want to, this is another example. So you are getting some photo, you want to say whether it is dog versus cat. Say dog is 1, cat is 0. And then you have some features. For example, what is the shape of essentially the ear? Or what is the shape of the nose? Or what are the colors? all of them, you can give some numbers or you can give some values. So color red, blue, this, for example, dogs tend to be, I don't know, maybe different color than just cats, which are more like black and white. And you will have the values for each of them. What is the shape of the nose? Is it like more dog style or cat style? Or any other things. Each of them would be the features that we are doing. And at the end of the day, you want to say dog 1, cat 0. Good. So every machine learning you can consider actually as a simple game, for example. In this case, it's a simple game. It can be regression, which is not a simple game as well. And the question is that each of these features, you want to say which one is more important. All these different machine learning algorithm is try to find different ways to guess F. And we have different algorithm again. We have linear regressions, we have decision trees, we have random forest, we have XGBoost and LightGBM. These are like some of the best ones, and there are some others like the neural nets, etc. But generally, like XGBoost is the one that the people use a lot in practice, or LightGBM. Now, having said that, someone said that I want to see how much the color of the dog is important. Color of this color of that animal is important in predicting that whether it is dog or cat. And by the way, you have this trained data, somebody essentially has some kind of label data. Somebody gave this one. For these X ones, that was the result was dog or cat, etc. And then for these guys, you don't know what is Y. So if you consider this one, this is for Y. For this one, you know that 1, 0, 1. But for these guys, the Y is unknown. And also for this future one, also 1 is. But that's the whole idea. The whole ML is understanding this function F. It's the features that are doing that. Now, there's a paper that essentially says that you, independent of which model you are using to guess F, you can find the importance of each of these guys. How can you do that? Essentially, you will find the Shapley value of each of these features. And that turned out to be, I mean, there are some justifications why like this kind of fairness and other things should be good. But in practice, that's actually very well-known fact. I mean, that the people tried a lot. It seems that very good, you can get a very good understanding about the importance of each feature. So essentially, importance of the feature would be the Shapley value of that. And this is, as I mentioned, there is one, and this is global. It is independent of which model you are using to get F. Based on that, actually, you can compute this importance of each feature. And this is something that you can compare now different things. And this is important. If you know which features are important, those that are not that important, you may want to remove it. Especially if you have time constraints. You want to make a faster algorithm, you may remove those guys. That is, like before neural nets, and even now with neural nets, one of the main things is that the people should understand what are the important features. The features that will be beneficial to deciding whether it is dog or cat, and include them in the machine learning approach such that you can get the best result with the as least as possible computational cost. And this is the one that is doing, and if you search, there is a Shapley value. There's a Python package that computes for you. You can do it also efficiently. This one that we are doing, if you consider computational issues here, it is a bit like high because we have n factorial essentially here. And then you need to go over all n factorial, all s's essentially. All s's, we have 2 to the n s's. But you can show that if you sample from this s's, you don't need to go through all of them. Sampling gives a very good 1 plus epsilon approximation. Somehow roughly the ideas. So there are better and more efficient way to compute it. Because again, the running time of this one, you need to compute all s's, and all s's, that would be 2 to the n. So the running time is not great, but you can actually do sampling. You don't get exact, but you get 1 plus epsilon, which is good. And you just don't run it for every s. You will just run it for some sample s's. That's the general idea that works in computation of this number. Generally, you don't need to do all of them, just take some samples of them. And that's the thing that currently is in use. There's a package, Python package that you can use it and do that. So you see, game theory is at work at MLS. And there are some other concepts. In general, actually, it is very useful. There are lots of intersection between ML and game theory. And if you, some of these top conferences in ML, like ICML or NeurIPS, IPS, there I think because it was NIPS and then it has been changed to NeurIPS. In this, both of these conferences, they have actually a special track for game theory and the things that we are considering. Coalition game theory in some sense, submodularity, etc. as well, because of the lots of relation between these. There is another concept called price of total anarchy that we are introducing that one in 2008. And interestingly, actually, that also has, we are using some kinds of a regret minimization algorithm, and this regret minimization in terms of the equilibrium. And that's the generalization of Nash equilibrium. That's another one that actually has been considered by lots of other people and extended the thing. So there are lots of things, as I mentioned, that you can consider those one and then consider the game theory version of that, like game theory version of ML algorithm or vice versa. They have lots of interactions. Good. And now let's go to the next one. So what about the stability of the Grand Coalition? So if you remember, that was the whole goal. We tried to get a Grand Coalition. Grand Coalition means everyone is included. However, agents have incentive to form the Grand Coalition if and only if there aren't any smaller coalition in which they could get higher payoffs. Because then they will go together, and why should we all divide the money equally? This is the case that, for example, you will see it in the House or Senate is happening. The people are not dividing everything equally. If they have the power, they will get everything that they can, as much as they can. So sometimes a subset of agents may prefer a smaller coalition. So let's see this example. Let's see the Shapley value for these guys. A gets 50 million, B, C, and D, they get 16 million, around 16 million. So of course, A on its own cannot do anything better because it is only, if you remember, it has was 45 and then it was 25 and 15 and 15. Correct? That was the numbers that we had. So A, B, C. A cannot do anything better. But A and B have incentive to defects because they have essentially they have enough number of people, more than 51, of course. They can just defect and say, oh, we don't need you. We are going together. This is exactly the thing that happens, for example, in a, say, for example, in Congress. Then they have incentive to defect and divide the 100 million among themselves. So how can they do get it? A gets 75 million, B gets 25 million, which is both more than for A is 25 million more, and for B is like around 9 million more, or 8 million more from the one that they got it in the fair things. So this is the question now. Okay, we define the Shapley value. Shapley value has this one. It is a pre-computation, is divide the money completely among them. So in that sense, it is good, it is efficient. And also it satisfies these three axioms. But still, one important thing is the stability of the coalition, that this guy may not want to be with this coalition. There is not enough incentive for us, for them to be that. So this is another important thing that happens in game theory, and the important one is the core things. So the core of a coalition game includes every payoff vector X, every, in a sense, feasible payoff, because we don't have money more than the money that we get it as a whole. The coalition does get the new of that coalition, essentially. That gives, so here, that every payoff essentially function, that every subcoalition S, uh, that gives essentially every subcoalition S at least as much in the grand coalition as S could get it by itself. What's the meaning of things in terms of formula? So this is all feasible vectors. Again, all feasible means that some of this xi should be less than essentially nu of n, such that for every S subset of n, the value that these people get, the sum, is at least nu of S. But why do we define it? Because then if we have such kind of vector x in the core, we say that vector x is in the core if we have this property. So then no S has any incentive to deviate from grand coalition. Because if you go alone, a subset of them, you don't get anything better. Also, that means that if X is in the core, then X is efficient. Why? Because we knew that, I mean, like it is a feasible. So one thing we knew that the sum of this xi would be less than nu of n. At the same time, because of if you put s is equal to n, then we know that some of them is greater than nu of s. So essentially, both of these means equality. So essentially, just the fact that we are talking about the feasible solutions, that also, and then we have this kind of core condition, it implies that they are efficient. It means that they are dividing the money exactly the same amount that we got it as a payoff forces. Good. So let's go back now to the concept that we knew before. Core, what was the idea again? The core is that if you just divide the money arbitrarily, then some people, they don't want to join the coalition. They say, okay, I will go together and we get a higher payoff. Core try to prevent this, so that I want to divide the money such that every coalition gets at most the money that I'm giving in total to that coalition in my somehow set of distributions. Very similar to the concept of Nash equilibrium. So that was the idea of Nash equilibrium, is that no person can do better by deviating from equilibrium. The difference is that somehow Nash equilibrium was the easier concept to satisfy because we talk every agent. If other people, they don't want to change, I don't want to change. So I'm talking about one agent. Here we are talking about coalition. In some sense, we are talking about collusion between several agents or lots of agents together. So in some sense, the core condition is much stronger because it considers the collusion. So the collude means several agents together essentially are coming and get things better. So if you want to define, maybe you could define a strong concept of Nash equilibrium. I think that strong maybe is a bit different from the strong that we define, is in which we say that this is an equilibrium in which no coalition of agents can do essentially better by deviating. So if you define a strong in this way, then this is some kind of a strong Nash equilibrium. Because that not only you cannot get it alone, something better, but if you go as any subset of you go collude together, still you cannot get anything. So this is the good or bad part about the core. So for the Nash equilibrium, that was the great theorem of Nash. Again, I mean, these are all these famous people that several of these that we talk about it, they had this concept of equilibrium, and you can get a Nobel Prize for that because these are like the interesting thing. So we talk about like Nash versus Shapley and others. So, and here, what was the important thing about the importance of Nash equilibrium is that under like the regular thing, there is always a mixed Nash. So there was not necessarily a pure Nash. And we don't know how you can find a mixed Nash in polynomial. That's also, this is some big open problem for computer scientists. But the issue now for the core is that the core might be actually empty. At least by Nash, thanks to Nash theorem, we know that there is one that exists that is a Nash equilibrium, but we may not be able to find it in polynomial time as of now. But core, it might be empty. So it means that whatever you want to do, divide this money, there is no way that you can make this one essentially something that these people deviate. Always there are some group that they will deviate. So these are not, if we can make some games, we can put some natural conditions, say for which game actually this will not happen. That would be the main question that we are talking. So essentially the question that for which game the core exists or does not exist becomes the most important. So let's see some examples here. So this is a good example of an empty core. So consider again the games before that we had. The Shapley value of A, 50 million, B and C, each of them was around 60 million. So the minimal coalitions that achieve 51 votes are this: A and B, A with anyone essentially, and like this either A or B, C, D together. Now, I want to, this is essentially the way that I can argue and say that core is empty for this one. It doesn't matter how do we divide the money. There are some people who are debating. And this is the proof for that. So say that if the sum of the payoffs to B, C, and D is less than 100. In this case, of course, it is like, I don't know, 16.33, almost like 49 million. Then it is, or like 50 million actually. So in this case, if the sum is less than 100 million, here is only 50 million, then this set of agents has incentive to deviate from the grand coalition. Why? Because if it is less than that, these guys, they can go together, they can get 100, even 1 penny more, $1 more, or 1 cent more. If they can get it, this extra money, they can go, whatever they will get it. In this one, it is 100. Everyone gets like a little bit of this 1 cent. Again, you may define to some kind of epsilon Nash with some larger epsilon that you can define it, and these are some research that you can do it. But for now, it is just a strict 6. So it means that if X is in the core, then X must allocate 100 million to BCLT. Then in this case, if they get all of this 100 million, then A gets 0. Does not have any incentive to join any of this goal, essentially. I mean, does not essentially wants to be in this thing that I have the 45 and got 0 essentially out of it. Then what does it do? It tries to join essentially with either B or C or D. And this is the interesting thing. So so we mentioned that it surely, if there is a core, it should give 100 million there. Now I want to get a contradiction. So if I give all the 100 million there, now if this is essentially this 3 guys get 100 million, one of them gets at most 33.33 million. Good. They got 100 million. One of them get at most this number of millions. Now, I say, why to that guy? Why do you want to go with them? They gave you 33 million. I can just, let's come together. I don't know whether B, C, or D, any of them. But there is one of them that is less than at most this one. That guy A goes to that, so okay, you get 33 million points this one at most this. I will give you 35 million. Then come and join with me. Then they will get it together. And then, and then of course, they can get, say, anything more than that is enough for this guy to convince, but can give a little bit even more incentive. If you consider epsilon Nash essentially, that the people don't want to change if the move is only epsilon beneficial. It's not epsilon. You can get even 5 million more to essentially. Yeah. So in that case, then the things that will happen is that so then A and B, they can just go together, And this essentially shows that A can always deviate from this one. And so it means that there is no essentially core, or like there is no vector X in the core. Good. So we talk about this thing, the core thing, and the core thing, as I mentioned, for this particular voting game that we mentioned, it is empty. Now, this is the interesting thing. Let's see what other games. So the question is that we are going to find some games for which the core is non-empty. So simple games. So these are some of the things that we are talking. So you want to say for which game the core exists or does not exist. Recall that G is a simple game if for every coalition S, the nu of S is equal to 1 or 0. The player I is called the veto player. These are all concepts of essential thing that you are seeing. Veto player, if the nu of S is equal to 0 if S does not contain I. So to win the game, then you need me. This is the theorem. In a simple game, the core is empty if and only if there is no veto player. And this was the idea. If you see this game that we had this essentially the previous game that we taught A, B, C, D, and then it was these things like the 45, 25, 15, and 15. There was no veto player. Why? Because there was this coalition of B, C, and D. They could go together and essentially make the things. This is the proof is very similar to that actually. Why this theorem is correct? It's a good exercise. The same way that we have proved it, you can see that why if there is no veto player, then there is no core essential. Now go to the next case. Okay, now what about the reverse? So this is essentially for this kind of simple game, we have a good understanding about core. Because the question is that when it exists, when it does not exist. The same thing that we talk about Nash equilibrium, correlated equilibrium, everything. But when it exists, when it does not exist. Or pure Nash, for example. In a simple game in which there are veto players, the core is all payoff vectors in which non-veto players get 0. So if there is no veto player, there is nothing in the core. We cannot essentially divide it such that no one deviates. But if there are some veto players, anything that you will divide between these guys, and you all payoff vectors in which all others get 0. This guy, you can't divide anything among themselves. Why? This is actually a good example. Consider the modified version of the voting game that we talked. Now, instead of this happens essentially in lots of cases, it is, I think, 80% get the thing. Some cases, I don't know, 66%, maybe 75%, but that is typical. Sometimes you need higher majority to change the thing. For example, if you have a Senate, generally you want higher. If you want to change the rules of the Senate, you want a higher essentially vote to change the rules of the Senate, because that affects also the voting. But anyhow, here we say that I think 80% majority is required to pass the bill. Actually, an 80%, correct. So here it says that 80% essentially is required to pass the bill. Now, what will happen? So ABC, they had 45, 25, 15, and 15. So the minimal winning coalition in this case are ABC and ABD. All this winning coalition must include A and B. So A and B are both of them are veto players. And note that they are both of them, not just A. So the core includes all distributions of this 100 million among A and B. Everyone gets, essentially, everyone else gets 0. The issue is that, I mean, you may give essentially $1 to B and then the rest to A, or vice versa. Still, it is in the core because these guys, they don't have any other option. Because both of them are veto players. That's the idea. So for simple games, actually, we have a very good understanding. What are the cores essentially? If they are veto players or not. In some sense, it is like make it a bit more, say, oh, this is just a trivial case. If they're veto players, then we can do it. If not, there is not. Maybe the core concept is a very good concept to have, but we don't have any like good things maybe it does not happen that often essentially that we have a core, non-empty core. So this is now let's consider this one a bit more general. Non-additive constant sum games. So non-additive constant sum game. Recall that the game is a constant sum if the nu of s and nu of n minus s is equal to nu of n essentially. It is additive if nu of s union t is equal to nu of s plus nu of t if s and t are disjoint. So this is the theorem. Every non-additive constant sum game has an empty core. So consider, so if it is non-additive and constant sum, it is like this. Non-additive at least means that what's the meaning of non-additive? It means that at least for at least for two sets S and T, we don't have this relation. Let's see an example. Consider a constant sum game in which there are three players. I'm giving the example such that you will see that, but actually you can get a full proof, the exact theorem out of this intuition. So here we have the V of A equal to 1, V of B equal to 1, and V of C is equal to 1. And like nu of these guys. And nu of ABC equal to 4. Note that here this game is not additive because here, if you get essentially nu of A plus nu of B and C is equal to nu of AB plus nu of C, and all of them are equal to 4. But the nu of BC, it would be equal to 4 minus 1, which is 3. Because it's a constant sum game. And then it is not equal to nu of B plus nu of C because that is 2. Yeah.
Therefore, A is a super additive.
I mean, no. If this is just for one set, it is the case, it's not super additive. You can have some less, some equal. When we say that sub or super, if all of them are less than that or all of them. Here you can see that some case it is not the case. So G here is non-additive. So now consider essentially X like this one. Equally essentially divide between this ABC because everything stays symmetric. Here you can see that the nu of AB here is 3. So here A and B can deviate and they can allocate 1.5 to 1.5 essentially among themselves. So if it is the case, you can say you start with this one, then don't deviate for this guy, you can increase them. So you can increase A and B to 1.5, 1.5, then you will give 1 for these guys. But if it is 1 for this guy, then A and C, they can deviate, and then A can get slightly more, and also C can get slightly. So this is the idea that essentially, if it is non-additive, if there is only one non-additivity at one part, you can essentially shift these things such that, and you are using this non-additivity and say that essentially you can always, there are some groups that they can deviate. This is something you can check it more. Let me just... But this is the interesting. So this is one of the most important theorems that exists, and that mentions that now essentially these games that we are considering are actually the core is interesting concept. So you remember that the game, it was supermodular or convex. If for any S and T, nu of S union T is greater than nu of S plus nu of T minus nu of S union T. And we talk about the marginal, the way that you can talk about marginal definition previous time. This is the main theorem. Every convex game has a non-empty core. Not only that, in every convex game, the Shapley value is in the core. That's the reason this kind of supermodular or convex games becomes important. Why did we define it? Because these are a special class of, these are actually a large class of games that we have this property for them. For these games, they are non-empty and Shapley value is in the core. So what's the meaning of that? It means that Shapley value, in addition of all these interesting properties that it has, also make sure that it is some kind of Nash equilibrium or equilibrium in some sense. So Shapley value becomes important because that gives you an equilibrium concept to you, essentially, that no one wants to deviate. And this is, just one example of this game. So this is just an example. So if you just change the modified parliament games, so we had 100 representatives, each of them have this number. Let's change the new function. Any coalition of parties can approve a spending bill worth essentially 1,000 times the number of representatives in that coalition. So essentially, we are defining this one. This is the nu of S. For any S, it would be 1,000 times psi 1. So here, nu of A would be 45K, nu of B would be this, nu of C this, and the nu of AB would be 70K because they have 70 members there. And this one. This game actually, you can say, is actually additive by the definition that we had it. And it is a convex game, like additive were essentially a special case game. So this is, of course, this is the one that you will do that. Now you can compute the Shapley values. And the Shapley values, actually, in this case, the Shapley values that you compute for them becomes A comes to 45K, B becomes 25K, C 15Ks, and D 15Ks. So interestingly, in this case, would be just the number of the things times K. Because this game was an additive game, essentially. And so you can see that, in this case, you can essentially check that anyone, if it goes to the other things, if there is deviates, they don't get anything better because of the definition of this new function, because that's additive. Shapley values also is 1,000 times the number of them for each of them. So essentially, it means that if you deviate, you cannot get anything better. And again, this is the thing, you may get something equal, but you cannot get anything better. This was a game, this was an additive game that it was there, but convex games are much more general than additive games. So there are non-trivial games, lots of non-trivial games in this class of convex games. And this concept of core essentially is something that says, at least is not some kind of obsolete concept or some kind of trivial concept that almost all the time does not hold. And when it holds, it is trivial. It is not the case because for convex games, there are several other cases that also the core is non-empty. So this is one area that the economists actually, some computer scientists actually thinking about that. What are the cases that the core is non-empty? Because core is non-empty is very important. It gives some kind of a strong Nash equilibrium concept that no subset of these guys they can put. So this is essentially the end of this session that we talk about this kind of coalition game theory, and the concept of equilibrium is this kind of this. And with all this definition that we had we used it essentially to get some interesting things. And as I mentioned, in particular, Shapley value is the one that is defined there. It has a lot of application now in ML, and the people are using it a lot in industry. So I stop here.